of all, let me welcome again Professor Elie Zeid from Princeton University. As you all know him, I'm just spending just a few words. First, again, for thanking him. He's the very first host that we have outside from Europe, so that's in any case a good signal itself. But then he was so kind and generous to share his time with us and to give these two seminars, let's say, to the PhD, and I see that they are, a relatively large number to be a PhD course, also thank you for participating. Professor Zeid is Professor of Civil and Environmental Engineering and Director of the Program in Environmental Engineering and Water Resources at Princeton University. He got his PhD in Environmental Engineering at the Johns Hopkins University after the Mechanical Engineering Master at the same Johns Hopkins University. He's also the chair of the Princeton Metropolis Project, a huge project about the management of the urban systems he will deal with during these talks. And his research focus is on the integration of theory, numerical simulation, and experimental observation to study flow and transport in the lowest layer of the atmosphere where humans live and have a direct impact on the planet. His work extends from the fundamentals of the turbulent flow and heat transfer in that layer to various applications, including the built environment and its environmental quality, energy efficiency in buildings, urban sectors, urban sensors networks, and air design. All these topics, that are of interest for the PhD course in energy and sustainable development, and they are specifically our research focus. So I hope you enjoy, and I really thank you, Elie, for your time and for coming and giving these lectures.
Thank you for the introduction, and Laura, it's always a pleasure to come to Italy and to Perugia and see all the exciting work that you guys are doing here. And so it's a pleasure to give these lectures. So to give a little bit of background, this is a course I prepared last year and during COVID, so it's all designed to be online. So Anna Laura may already have sent you the link. So these are, today it's kind of a summary of 2 lectures, and Friday is going to be a summary of another 2 lectures from the course. But all the lectures are actually accessible online. And they are formulated usually as a recorded slides that you watch before the lecture, and then in class I gave a Zoom lecture, and that Zoom video is available there. So you can basically see the, some of the other lectures and topics I covered. So after discussions with Anna Laura, we decided to focus on 2 topics related to energy budgets and radiation. But first, in this course, always I give a picture in the background of a city, and I ask the student if they can recognize which city this is.
Pittsburgh.
Pittsburgh? No, actually, it's, now that you mention it, it's very close. It has the confluence of 2 rivers, but no, it's actually much closer to Perugia.
Cairo?
Well, not very.
Cairo?
Cairo. This is Cairo, actually. So Cairo is the largest city. Well, the largest city in Egypt, obviously one of the largest in Africa. And one of the things that you observe in this picture is that it's built on a river. Like a lot of our cities are built on rivers and close to the coastline, and this makes them particularly sensitive to issues of floods or sea level rise. So being close to water is one of the sources of vulnerability of a lot of these cities. So the first topic today is then going to be on, it's not work, on energy budget and heat transfer in city. And my work is not really on the building, but more on the city. So I know a lot of you work more on the small kind of building neighborhood scale, so you can see how your work relates to the bigger energy budget in cities. Here, maybe it will work. Okay. So just to recap, you probably have seen the recorded slides I asked Anna Laura to share with you. And basically this is just kind of covering the basics that you probably know, just to refresh your memory. It talks about the various forms of energy, thermal, potential, kinetic, and here we're mostly interested in thermal energy. and how it's transferred as heat in the city. We also talked a little bit about energy conservation and budgets and the first law of thermodynamics. We talked about thermal energy because it's the most important for urban microclimates, and in the recorded slides also we talked about cold and heat waves remain the most consequential natural disasters in terms of the impact on human lives and mortality. So basically, to summarize, you can, this is a simple expression of an energy budget. You're saying that the energy at the time t is the energy at the previous time, plus any energy or work entering into the system, or minus energy and work leaving the system. So this is very simple, and you can divide this by the time span over which you're evaluating this budget. So you get something that looks like, if this is energy per unit time, so this becomes an equation of power. Power is energy per unit time. And then you can basically think that, okay, if energy if the thermal energy H is the only thing that is changing or flowing in and out, then I can basically say that the change in energy is really only the change in H, because let's say there's no chemical or nuclear reaction or phase change. So all the other energies are constant, and H is the only one that's changing. You can then say that the rate of change of the thermal energy is the thermal energy in minus the thermal energy out, also expressed in terms of rate. And finally, of course, you can express this for a kind of, in the limit of dt going to 0, to get kind of a differential equation expressing dH dt in terms of the rate of H going in and out. So this is kind of the simplest expression of an energy budget, a thermal energy budget of a system that you can express. And of course, sometimes you might have energy sources or sinks that you might have to add here. Now, thermal energy is simply an expression of the kinetic energy of the molecules at a microscopic level. And that is basically what temperature is expressing. So temperature is really just a direct measure of thermal energy. And the relation between thermal energy in joules and temperature is given in this equation. So if you multiply the temperature by the heat capacity in joule per kilogram per Kelvin and the mass of the system in kilograms, you obtain basically the joules in the system. So you can express the thermal energy content either in terms of temperature, if you know M or C, or in terms of joules. So then if you basically write H as mCt, you can rewrite this differential equation in terms of d mCt over dt. And if you have a system that's constant, let's say a roof, the mass and thermal capacity might be constant, you can take this mc out of the equation and write of the derivative and write the equation like this. Now, here's a question. Let's say we are interested in the very, very outer facade of a building. So I'm talking about something maybe as thin as this layer, not the whole wall, right? Just the interface between the building and the atmosphere. So this, you can make it arbitrarily thin to the point where the mass is essentially negligible. The mass is going to 0. So what happens with this equation if the mass goes to 0? Very simple.
0.
0. So right at this whole term becomes 0 because m is 0 and c and dt are finite, so it has to be 0. Now, so if you say that this is 0, basically it means that Hn is minus H out is 0, which means that the heat going in, the heat rate going in minus is equal to the heat rate going out is equal to 0. They are equal, but they're not equal to 0. And basically dt over dt is not 0. So when you set m to 0, you're saying that the sum of these two is 0. So they have to be equal, but each of them is not necessarily equal to 0. It could be, but not necessarily. And when you set also this is equal to 0, remember that it is m that's equal to 0, not the time rate of change. So this is a very important surface energy budget concept, where you're saying that if you take a very thin surface between the building and the atmosphere, or between any ground layer and the atmosphere, that basically in the limit of a very thin interface, the mass of this interface is so small, such that basically the change in the stored energy, this is the change in the stored energy, the change in the stored energy is negligibly small, because the mass is going to 0 even when the temperature of the interface changes. So even if the interface heats by 5 degrees or cooled by 5 degrees, this heat change content is negligible. And as a result, the heat going in has to be equal to the heat going out, roughly, because the imbalance between them is this very, very little term. Now, why is this important? So this is important because if we can say that, let's say for the very thin interface of a grass surface with the atmosphere, if the interface is very thin and Hn is equal to H out, then basically we can write a budget of what goes in and what goes out without considering the change in the storage. So we can say that, for example, in this picture, typically in the atmosphere, we have radiation coming in as Q star. This is kind of the net radiation term. We have the heat being conducted into the ground, which we call Qg. And we have the sensible heat QH. This is basically the heat that is transported between the surface and the atmosphere. So this is the convective and diffusive heat transfer. Molecules of air touch the surface, pick up some thermal energy, and move up. So this is kind of the sensible heat that you feel, because it raises the air temperature when the surface is hotter than the air. And this is the latent heat flux. So the latent heat flux is the one related to evaporation. So a joule, you put a joule into the surface, and then this joule is converted to break the hydrogen bond and evaporate the water. And then the water vapor molecules leave. So basically the energy left the surface, but it left as water atoms that have higher energy because they're in the gas phase. So we call it latent energy, latent meaning in Italian probably the same, latente or latente probably. So it means you cannot feel it. And you cannot feel it because basically you don't feel that the temperature of the air has changed. It did not go up. However, the air has more energy because basically it contains these water vapor molecules that if they come back together and condense, this energy can actually be released. So you can recover this energy when you get precipitation. So this is basically the surface energy budget that is the basis of a lot of, let's say, environmental models or Earth system models for a lot of vegetated systems. Vegetated systems or natural systems are easy. It's just kind of an interface, let's say, between desert or water or ice and the atmosphere. And remember that, again, heat going in is equal to heat going out, but the temperature of the surface can be changing. But if we're considering a very thin interface, that energy that's required to change the temperature is so small, such that what goes in is roughly equal to what goes out. Okay? So again, this is kind of what I already explained. So Q star is the net all-wave radiation, which is positive during the day. Qg is what goes into the ground. QH and QE are also what goes into the ground. So notice here that we have a very specific convention for science with this surface energy budget that you'll see it in urban or natural application. The convention is the net all-wave radiation. We're going to define it as positive if it goes into the surface, while the ground heat flux, the sensible heat flux, and the latent heat flux, we're going to define them as negative if they go into the surface. Why? There's no reason. Some very few references will define things differently, but in most of the textbook and paper, this is the definition. So if this is the definition and what goes in is equal to what goes out, then you can say that Q star must be equal to QH plus QE plus QG, meaning during the day, the energy that goes in by radiation from the sun and from atmospheric radiation, minus the radiation that goes out, which is this Q star, it's still positive. That's a source of energy heating the surface. And this energy going into the surface as radiation, leaves as conducted heat to the ground and later insensible heat to the atmosphere. Clear so far?
Yes.
Okay. So let's talk about each of these components a little bit in more detail. So the radiation component, you guys here work a lot on radiation, so you know this, but a quick reminder. So typically we try to divide atmospheric radiation in a simple way into short wave, which is the solar radiation, and long wave, which is all the terrestrial radiation. Solar radiation well, we're going to talk about this in a minute. So S is solar short wave radiation, and L is terrestrial long wave radiation. Now, in reality, at any given surface, the biggest source during the day, the biggest source of energy coming in is this incoming short wave radiation, and this can be direct from the sun, or it could be basically solar radiation that got diffused or diffracted in the atmosphere, and so it arrives as diffused short wave radiation. But both of them together are the short wave down, and in Perugia and Princeton, that could be something on the order of 1,000 watt per meter square. Then some of this incoming solar radiation gets reflected, and alpha S is the surface albedo or reflectivity. There's a little bit of difference between them, but basically this is the fraction that gets reflected. And so what gets reflected is alpha S times S down, and this goes back up to the atmosphere and maybe to the outer space. And then L down is the downward long wave radiation coming from mostly the H2O and the CO2 in the atmosphere, and also from clouds. And finally, the long wave up has two components. First, part of this long wave coming down can be reflected, and here you have to use alpha L, which is the albedo for long wave radiation, because a surface will have a different reflectivity for short wave and long wave. So this is alpha L, this is the albedo of long wave radiation, the fraction of L down that's reflected. And also, like any surface, as we saw in the recorded slide, like any body, because the surface has a temperature Ts in Kelvin, it's going to emit like a gray body, where alpha is epsilon is the emissivity, sigma is the Stefan-Boltzmann constant, it's a universal constant, and this is the amount of energy that is radiated by the surface to the atmosphere. Now, it turns out by Kirchhoff's radiation law, and if you can Google it, I don't know if I cover it in the slides of these two lectures, but Kirchhoff's radiation law tells us that alpha L for long wave radiation has to be equal to 1 minus the emissivity. So in that case, we can get rid of alpha L and write it as 1 minus emissivity, and here we have emissivity, and so we have a expression for long wave radiation up that only depends on basically the surface property, that's emissivity, and then sigma, which is the universal constant, and the temperature on the surface, and L down. So this is basically how we can compute and measure the net shortwave radiation. So again, to give you, so this is about, let's say, 1,000 watt per meter square. Let's say the reflectivity is 33%, so 333 go up, are reflected, 666 are absorbed. And typically L down and L up, actually, if you take the difference of the two, typically they balance out, and they often could be like 300, 400 watt per meter square, but typically they balance out. So not under all conditions, but typically they balance out, and so even though this is 400 and 400, the difference between the two is actually not a huge contributor. Okay? Clear so far? Okay. So now let's consider a roof during daytime. So what we're saying is that there's downwelling shortwave and long wave. and part of it gets reflected and emitted. So we end up with this net radiation. Try again. Let me try something else. So I can try that. Yesterday we did maybe the VGA is
Can you hear there's something like, can you hear that maybe it's overheating or not? Because I can hear the,
but it's still on. It's kind of, well, I mean, okay, so yesterday what worked is to turn it off and on.
yeah, maybe it's like, I don't know if there's a ventilator inside because I can hear it.
But they should, I mean, it's normal that it's like, you know, ventilating. So I don't know. So I don't know.
So now he's connected with the video.
So that's connected with this. Is the
No, I think because I can hear like, there's like something. I would spend that anyway.
that's the double. Can you give me back the USB actually?
Like it pulls and then.
Sorry, the HDMI. The HDMI.
Yes.
Sorry about this technical glitch.
No, it's,
I wonder if they are still inactive.
yes,
They are.
they are. But we don't see the screen.
Okay, that's fine. So I don't know which source would be. Everything is off. So maybe I could, you know, I could try to use this computer if this is. Oh no! Now I see my my thing here. So that's not what we want. Maybe. I think what we might want is actually this one. Would like So, just like one more.
Okay.
This looks good.
Let me see what they see. If you get connected, so at least I can see from the page.
So if we just not disconnect the camera, it should be good.
You see? Yeah.
Yeah, I see the webcam. Not the sharing screen, just the webcam.
Okay.
Okay, so sorry about this technological glitch. I think certainly the VGA was more stable than the HDMI yesterday, so that it should not happen. Okay, so this is the Philip Johnson glass house. If you go to New York, it's close by. You should go and see it. It's quite interesting. It's all glass except basically the roof. So for the roof, we said we have downwelling and shortwave and longwave, upwelling, shortwave and longwave. And for this house,
The
this,
audio is out.
the audio is off.
Okay, thank you.
Okay.
It works now. You hear us?
Yes, yes.
Okay.
Hear you.
I don't know.
Yes, exactly.
Okay. Okay. So then, okay. So this is the main source of energy. And then what will happen is some of this energy will go through the roof and then eventually make it into the house. And then some other sensible energy will go into the atmosphere, increase the temperature of the atmosphere. And some of it, if the roof is wet, will basically go into evaporation. Now, this is all kind of during the day. So what happens at night? And of course, this is the equation. So at night, everything kind of reverses. So notice that at night we don't have shortwave radiation. The sun is gone. So basically, you have downwelling long wave from the atmosphere, but the roof is hot. So the upwelling long wave is actually going to be larger. So what's going out is more than what's going in. So the net radiation is going to be negative, meaning on average, the net effect of radiation is to cool the roof. This is what we would call radiative cooling. Now, where is this energy coming from? So you would notice that the roof has heated up during the day, so it's now releasing its heat. So Qg is negative because Qg goes into the interface, and by the convention, we said going into the interface is negative. So negative meaning it's a heat source to this upper interface. So it's negative, it's going up into the interface. And you will notice that typically the surface is going to be cooler than the atmosphere. So typically QH is going to be negative, meaning it's going, again, the air is heating the surface. But that's not always the case. It could be the other way around, but typically the heat is going to go from the air to the surface. And evaporation, if the roof is still wet, it might still evaporate, so you get a positive QE upwards. And if you have dew formation, it's the opposite. Dew formation, meaning there's condensation onto the surface and basically negative evaporation. So this one could be actually negative, but most of the time this is gonna be zero or positive, and these are gonna be the main sources of energy going into the interface. Now you notice here that what happens is that the equation still works with the same definitions, but now the only difference is, unlike the day, all these terms are basically tend to be negative. So this is negative, meaning a heat loss by radiation, and this is negative and this is negative, meaning a heat gain from the atmosphere and the bulk of the roof, and this could be 0 or something like that. Is this clear? Now, you would notice that this storage that became a source of energy in the evening is very important when you think about the city. The nighttime urban heat island is mainly driven by all the storage heat QG that at night starts leaving the ground. So this is for the smallest or thinnest element of the city, just a little interface, let's say, between the buildings and the atmosphere. Now you can think at a much, much larger scale. You can think, okay, what if I have a whole city or a whole neighborhood, and I want to write an energy budget for it? What's happening? So now you can see the same terms. By the way, a lot of these plots are from the book of Oak, and I use the nomenclature of Oak. So you would notice that, again, you have Q star, QH, and QE from, let's say, this large plane at the top of our control volume. And we still can write something that looks like this energy budget, where we are interested in the change of the thermal energy content of this control volume over some time, so a change in the power, if you want. Now, what you would notice here is that when the interface was very thin, the mass was 0, we said the storage, basically this term goes to 0 because M goes to 0. But this is only for a thin interface. When you consider a big volume that has houses and trees and cars, obviously this is a system with a large mass. So the change in the heat content is no longer negligible. And now you should keep this change in the heat content. And you can say that this change in the heat content is the sum of all what goes in and what goes out. And as I told you, so this is basically the top 3 terms we've already, or this term and these 2 terms, we've already seen them. So this is net radiation going in. This is sensible heat and latent heat going out. But now we see also new terms. So the first ones we're going to see is QA in and QA out. A here stands for advection. So as wind goes in and out, it can pick up some heat and take it out, or it can bring in some heat. So the difference between heat going in with the wind and going out is QA in minus QA out, and that becomes a net source of increasing or decreasing the temperature and the heat content of this big control volume. This is the net heat transfer by advection. You also know that we have to add the term QF with it, which is anthropogenic heating. So chimneys, cars, building heating, all that contributes to emissions that we are sending or we're creating into this control volume. So this now also has to be included, and we call this QF. We're going to call this QF. So notice that we started with a thin interface, we got a simplified one, but when you go to consider the whole city, it becomes more complex, and you have to take into account anthropogenic heat and advective. Now, let's look at the surface energy budget in this example of basically four neighborhoods: Chicago, Tokyo, Vancouver, and Basel. And these are going from the least urban. So this is not all of Chicago. Chicago is very urban. This is one site in Chicago that has a lot of vegetation and very few houses. This has a little bit more houses, and building. And this area in Vancouver is the most urban. Let's see what happens to the surface energy budget terms as you go from the most rural to the most urban one. So you notice that Q star, these are all have the same scale. So Q star, the net energy is a little bit different, but it's not drastically different. So here it's 600, here it's maybe 650 or 700, here it's about 550. So it varies, but and that depends on the albedo and other things we're going to talk about. But basically, Q star for these 4 cases is roughly comparable. But you observe that, for example, if you start at the most rural or most vegetated site, you notice that QH and QE are equal. So the energy going into the atmosphere is half sensible, half latent, because you have a lot of evaporation. And you'll notice that as you go to the most urban, this balance completely changes. So here QH becomes larger than QE, which is the blue. Here the difference goes larger, and here QE is almost negligible, and QH is much, much larger. So you notice that as you go to areas with less and less vegetation, there is less evaporation, and more of the sensible heat flux that's going to heat the air, and this is kind of contributes to the urban heat island. Now, looking at the yellow, which is the storage, you notice again that in this suburban areas, it peaks at about 200 during the day, and it's released during the night. Here it goes a little bit higher, and when you basically, this is a little bit below 200, and when you go to these two most urban sites, you see that now this is about 250, so you have a little bit more, or appreciably more storage, and this is here, the storage is the highest for this most urban site of the four. So you notice again that when you go from soils to concrete, we're going to talk about concrete, it's a very good storer of energy. This heat storage increases, and that heat storage, it's stored during the day and it's released during the night. So it's like a thermal battery, right? And this release of heat is going to contribute to the nighttime urban heat island. You already noticed that the daytime urban heat island is mainly controlled by the lack of vegetation, which makes QH very large. The nighttime heat island is, on the other hand, controlled by the release of stored heat. So the physics of the nighttime and daytime urban heat islands are actually quite different, and that's why you need to think about them and about their mitigation slightly differently. So again, something very important that we define in hydrology is called Bowen ratio. This is the sensible over the latent heat, and as you go to more and more urban sites, this ratio increases. And again, you would notice the significant delta QS that becomes larger. In this case, let's say Q, you notice here that QG over Q star, let's say in this case the ratio is 0.5. Typically for totally vegetated rural area, this ratio would be about 0.1. So only 10% in vegetated areas or forest is stored. In cities, this could be up to 50%. So storage is much larger. Clear so far? Now, when you go and take a look at a lot of sites and you say, let me plot the vegetation plan area fraction, so how much of the surface is vegetated versus impervious, and look at the Bowen ratio, which is QH over QE, or at this kind of evaporative fraction, if you want, it's QE, it's the latent heat flux divided by Q star minus the storage, so kind of it's a normalized QE. You notice that basically the evaporative fraction increases linearly as you increase your vegetation, and your Bowen ratio, this is not linear, but it's neither logarithmic. I don't know what the scale is, but it increases from top to bottom. So you'll notice that for the most vegetated site, the Bowen ratio can be 0.25. So only 0.25, basically, QH is only a quarter of QE, meaning there's a lot more evaporative cooling. And as you go to the least vegetated site, this becomes 0.1, which basically means that 90% of your available energy is heating the air and only 10% is dissipated by evaporation. So vegetation has a big impact on urban heat islands and the surface energy balance. Now, to talk a little bit more about the storage term, it is large in cities because built material can store a lot of energy because of the high thermal effusivity or inertia or admittance. It has different names, it's the same quantity. So this is the square root of kappa m Cp, or actually the square root of kappa Cp only. So this is kind of the effusivity. I call it effusivity. Oak's book called it admittance, often it's called thermal inertia, not inertial inertia. Oak mentions also that wet rural soils, unlike dry soils, have actually a very large effusivity. But they also evaporate a lot, so QE is large. So even though they have a lot of effusivity and they can store a lot of energy, because they're also evaporating a lot, the storage will actually be smaller. Also, something that contributes to the storage is that complex urban forms allow energy to basically enter and be trapped in the urban fabric through something that we call radiative trapping. We'll revisit this next time. And this basically reduces the effective albedo of the city, favors absorption, and increases storage. So basically, all these factors lead to much higher storage in city. So let's look now at the anthropogenic heat flux. Now this is a big source still, like it's really difficult to predict and model it. We typically, in modeling, in large scale weather modeling, we typically try to estimate the amount of heat we should add as anthropogenic heat to models based on the density. So these are estimates that tells you that, for example, for large high density cities, it's on average about 60 to 160 watt per meter square. In the winter, because you're heating your whole houses, it's much larger, and in the summer it tends to be smaller. Medium density and low density, you notice that all these quantities decrease as basically you have less people and less activity that emits anthropogenic heat. This is also given in terms of what Oak calls the local climate zones. I talk about this concept in other lectures. It's not very critical here. But basically you see that when you go large, medium, low density, or a heavy industrial area, these decrease if it's residential, and if it's commercial, it will actually increase again to about 300 to 600 watt per meter square. But there's a lot of uncertainty, and this is a topic of continuing research if you want estimating QF. Now, so what are the main sources of anthropogenic heat in the cities? What do you think are possible sources?
Sun.
So anthropogenic, it has to be emitted by people and people's activity. Transportation, what else?
Power plants.
Power plants, what else? Cooling and heating, yeah. So let's take a look. So transport and space heating are obvious sources. So transport, all the heat from the engines and the exhaust. Space heating, we're heating here, and this heat is being conducted through the walls and going to the outside. So we're losing this heat. So that's a source of heat. Space cooling is surprising. You say, I'm cooling the space. How is that a heat source? But anytime you have some heat gain in the summer, you have your AC that takes this heat and pump it back out. And because the AC's efficiency is not 100%, it pumps it out plus the work penalty. So it pumps out more than the heat it releases is more than the heat that goes into the building. So it becomes a net source of anthropogenic heat into the city. And this is a plot of basically the energy consumption as a function of the average daily temperature. You notice that when you're in the region around 20 degrees, you have very little energy consumption. But as you go hotter, you have cooling demand, and lower you have heating demand, and that becomes a big source of energy consumption. And all this energy consumption is going to somehow become a source of anthropogenic heat. There's a lot of other sources: lighting, water heating, cooking, electrical appliances, industrial processes. Our metabolism itself is a source of heat. These tend to become minor, especially with better technologies there. So these remain the main sources. Now, you notice with transportation, the average efficiency of a gas engine is 35%. So 65% of the heat is actually released as anthropogenic heat. If you go to electric cars, Electric cars have efficiency of about 90%, which means that basically only 10% of the energy is wasted, and not all of it as heat actually. So you notice that if we electrify our fleet, the anthropogenic emission from the transport sector will be reduced significantly. Okay, this is again another plot of the QF of the anthropogenic heat as a function of population density. Obviously, if more people live in an urban area or in a square kilometer, more anthropogenic heat is going to be emitted. However, if you actually plot the, sorry, if you try to basically fit a straight line into this plot, you see that the slope has to be less than 1. Meaning that even in this case, I'm saying that you're going to increase the anthropogenic heat is going to increase with population density, even if the emission per capita is constant. But in reality, people that live in dense cities have smaller houses. They use less transportation. So QF per capita decreases with population density. So if it didn't, probably this graph would do something like that. But because larger cities tend to be actually more energy efficient, the line would have a slope that is basically smaller than 1 if you, if you normalize it, obviously. Okay? Clear? Okay. So this is kind of the end of the class lecture of 6. So here we're going to continue with energy, but this is kind of jumping into the next lecture in the course. So can you recognize this city? This is really closer to Perugia now. So it's Mediterranean.
Beirut?
No. I show Beirut in a different one. This is actually Marseille. This is Marseille. And Marseille is the oldest inhabited cities in France. It's the oldest city in France. It has, a longer historic record of inhabited than any other city in France. Okay. So we're going to continue with, again, talking about budget and heat transfer in city. So to recap, we talked about the interface. We talked about the whole city or the whole neighborhood, right? Now we're going to talk about an intermediate scale. So not a facet, not the whole city, but maybe a street canyon, right? So the street canyon is actually a very useful scale to think about. It was popularized by Tim Oak. Oak is really the father of urban climatology. And Oak's idea was to think, okay, let me not think about just a little facet or a whole city. Let me think about the smallest element of a city that, if you add a lot of these elements, you get the whole city. And we thought, okay, let me just think about 2 buildings and a street between them. Okay? And you can say that, okay, one area of Perugia has the same property, so the same height of building and the same street width. And then you go to another area. This is what they call local climate zone. You go to another area. The element still looks the same, but the properties change. The building gets higher, there's more trees or less trees. But you can think of your cities as neighborhoods with homogeneous properties of building height and street width. And if you can do that, then you can model it using this urban canyon concept. So many models, including some of the models we developed and that Elie and Claudia use this kind of urban canopy concept. So the idea is you have a very long canyon in the sense that the length of the street is much larger than its width or building height. So essentially you can think of this as a 2D problem. The edges are not as important. And you have buildings, you have the height of the building, the width of the building, the width of the street, the width of the building. In a modeling perspective, you can basically impose the temperature inside the building, and you can measure the temperature outside, and you're going to have heat fluxes through the roof that goes into the building, let's say during the summer, and through the walls. You can also kind of divide the roof into a green fraction, a black fraction, The walls, you can divide them into glass, brick, and stone, or whatever you want. And the ground surface, you can divide it into asphalt, concrete, and some type of vegetation. So this is kind of the street canyon. So the four elements are the roof, the ground, and two walls. You can treat the walls similarly, or you can say, I have a wall that's shaded and another that's sunlit. Each facet could consist of many sub-facets, and some of our models, like the one we developed, they don't have to be constant. Now, let's talk about each of these elements and think about its energy budget. So let's think about the roof, the whole depth, not only the interface. They tend to have an outer layer that's either black or white, consisting of an impermeable membrane. And white or black, the albedo will be very different. The outer layer may have very high thermal conductivity or capacity, but it's tend to be very thin. So this outer membrane is very thin. So mainly the albedo is going to control the exterior temperature. And this outer layer has the biggest control on the exterior temperature, not on how much heat actually is going to go into the building. It's just the membrane. Okay? The interior will consist of insulation material with very low conductivity or capacity, so you want a low effusivity. And this insulation layer will dominate the bulk thermal property and how much heat actually makes it into the building. It's going to have, you want something with low thermal effusivity and low storage. So you typically want to construct things that are insulating and not going to store a lot of heat to give you low delta QS. If you want to design the optimal, that's not always the case, right? Usually they're kept dry except for green or blue roofs. So typically from roofs, QE is very small except if you're after a rainfall or if you have a green roof. Albedo can vary widely. Of course, cool solutions and black solution is all about controlling the albedo. And one thing that's important is they have almost full sky view. So they tend to be not shaded, except if you're small house next to a skyscraper, the sky view factor is almost 1. Do you know what the sky view factor is? So it's very simple. The sky view factor is the fraction of the sky that you see. So if you're on the roof, you see the whole sky. If you're in New York between two skyscrapers, you see 10% or 5% of the sky. Right? So it's roughly the fraction of the sky that you can see. Okay? So during the day, they can produce a large QH. Remember, especially if they are very well insulated. If they're very well insulated, nothing can go in. So, and they are dry, so nothing goes in, nothing evaporates, so all the energy is released as QH. And at night, they will cool by radiation absorbing QH from the atmosphere. So the balance shifts. Now, here are some roof material, and let's talk a little bit about their capacity or thermal properties. So here, the heat capacity is how many joules you need to give them a meter cube of the material in this case. So this is the volumetric heat capacity to raise it by 1 degree Kelvin. The thermal conductivity is basically how many watt you can drive per meter of material thickness per Kelvin of temperature difference. The thermal diffusivity is basically, you probably saw it before, and the thermal admittance is what I talked about before. It's basically kappa Cp, but this is the Cp per mass. So so this is C times rho, right? This is the thermal admittance, and the diffusivity is simply K divided by Cp, right? So so kappa in this nomenclature, kappa is equal to K over Cp, right? Yes, I think so. Unless I confuse things. Okay. Now you have to be very careful with these things because if you think so, kappa, this is kappa and this is K, and this is big C tends to be the heat capacity per unit volume. Little c or little Cp in my nomenclature is the heat capacity per unit mass. So be careful, always look at the units. The units will guide you if you're confused about what different books or different papers are defined. Okay? Let's see. So, okay. So we've defined this, so let's look at these, at the values now. So let's say for the heat capacity, you notice that something like cork or polystyrene are used for insulation because they have a very low heat capacity. If they have a very low heat capacity, that will result in very low thermal admittance, which is great. This is what you want for a insulating material, right? Now, if you go, for example, to things like brick or adobe or clay tile, they might have a higher heat capacity, but also they have a higher conductivity. So with a high heat capacity and a high conductivity, they tend to have basically large values of thermal admittance, so you don't want to use those for insulation. This is going to be terrible for insulation because it can admit a lot of heat. And finally, plaster or gypsum are something in between, and basically you see that they are intermediate. So basically you see that some of the old material that we used to use, like clay or adobe or brick or plaster or gypsum, have very high thermal admittance, so they're not good insulators. So this is why old buildings will have these very thick, huge walls. So you basically increase the mass and the thickness to compensate for this large admittance. With the more modern material, polystyrene and cork, you can have a much thinner insulation that gives you a similar effect, because basically they both conduct less and store less, and this is a good, basically a good kind of combination to reduce the thermal effusivity and potentially the diffusivity. Okay. So, yes. Okay. So, from roofs, let's go to talk about grounds and pavements. So, like roof, they tend to be dry, except for in-canyon vegetation. But unlike roof, they're usually made of material that are not trying to insulate anything. So, they tend to have high conductivity and effusivity. And this is a positive property in pavements because you don't want them to freeze right away. So you want something that will conduct heat. If the surface freezes, will conduct heat from below, from the core of the earth. So you want material that's conductive. So the exact opposite of what you did for the roofs. So in the daytime, QG can be larger than QH because they are very good storer of energy. And so you're going to have a higher time storage, higher time flux into the ground, which is going to lead to more storage, and that storage is going to be released at night as negative QG, leading to the street level urban heat island. At the night time, all this large QG is going to be released and feeding QH. So now the heat comes from the ground, reaches the interface, and then released as sensible heat flux QH into the atmosphere, again resulting in the urban heat island. Now, unlike roof, they tend to have a very small sky view factor, especially when the building height is very large, and this results in radiative trapping even at night. The radiation, the long-wave radiation they emit, doesn't go into the sky. It's absorbed by the walls of the buildings, which then re-emit onto the ground. And so basically you get some of this long-wave radiative trapping. And the albedo varies a lot depending on if you have asphalt or concrete or stone or something else. Okay. Now let's look at some of the properties of the pavement material. Again, capacity, conductivity, diffusivity, and effusivity or admittance. So the first thing to note is in this case, oak. This is a table from oak. He gives the properties of dense concrete and aerated concrete. Aerated concrete is one with a lot of basically air and air bubbles in it. And you see that the difference is almost an order of magnitude. So when you talk about concrete, it's very typical to know what the properties are unless you know exactly how it was made and what's in the matrix. Otherwise, it can have a very large range of properties. Asphalt tend to be a little bit more kind of specific or narrow in terms of its properties, and stone and the other material can be different. But let's take a look, for example, at the thermal admittance of the ones we use typically, of the material we use typically for pavements. So both of them, you notice that have high heat capacity, and especially concrete also has a high conductivity. Asphalt has half of the conductivity of concrete. This is why asphalt gets very hot at the surface, because it doesn't conduct the heat down. Concrete remains cool, and stone remains very cool because it's highly conductive. But they have basically effusivities on the order of 1,000. And you'll notice that what we typically use for roof, we go down to, let's say, 25 or 100, so much larger thermal admittance. Clear so far? So grass surfaces in the city, they have a strong cooling effect because of the evaporative latent heat, QE. It's going to be very important for their thermal response. QE is actually further boosted in cities because it's like the oasis effect. So you have a little area that's wet, and around it everything is very dry. So the air coming in is very dry, and dry air is more able to absorb moisture from these wet surfaces. So the model of the oasis effect is the Boucher complementary evaporation model or concept. It tells you basically that the less evaporation is happening around a wet patch, the stronger evaporation will be from that patch itself. This is kind of an effect that happens in city with stronger evaporation. And so that's the oasis effect we talked about. And let's now compare basically some of the properties again of vegetated soils to roads and pavements. So you'll notice that here there's dry and saturated. And these properties are very different depending on if the pores are filled with air or water. If you reach the admittance, which is the most important, you can see that the admittance of wet soils, whether it's clay, sandy, or peat, is almost 10 times larger than their dry counterparts. So typically we think of soils as not having a large thermal effusivity, but if they are wet, they will. And you notice that this effusivity becomes almost as large as stone or concrete, which is a very large thermal admittance, meaning they're going to store a lot of heat. However, again, going back to my comment before, these are dry, so this is going to convert everything, all the energy input into storage. These are wet, so these are going to evaporate a lot, and only what remains is going to be stored. So even though they can store a lot of energy, or they can store as much energy as these, in practice they won't because they'll evaporate. Okay? Okay. So let's, for example, now look at this kind of the heat balance of asphalt versus grass, again from Oak's book. You see that in these cases, again, Q star is similar. So on purpose in this plot, they picked two areas that have similar albedo, so the Q star is comparable. You notice, for example, that for the moist grass, all of this energy input was dissipated by evaporative cooling, and only a little bit was stored and released as sensible heat. Here you have no evaporative cooling. You'll see that QH and QG are going to be much, much larger. And these are measurements, right? So what I told you is kind of theory. What you expect, these are actual measurements, in this case from Vienna. The road is in Vienna, and the moist grass is in Vancouver. So these are actual observations that have been repeated at many other sites. Okay, let's talk about the walls. This is something we need to take a little break. So let's get started. Okay. So let's talk about walls then now. So the energy balance of the walls is going to depend very strongly on the orientation relative to the sound angle, exposure and access to solar irradiance, which depends on shading, aspect ratio, and sky view factors. So multiple absorption of radiation can significantly increase the temperature. This is basically when you have in the canyon, for example, a ray of light that can hit the wall and be reflected once and another time. And so it's absorbed 3 times instead of only 1 time, for example, when it hits the roof. And walls, as you can expect, are made of a great variety of material and orientation. We will see later in the course, I don't know if we're going to cover this lecture, that some reflective properties of walls can be very crucial to the urban environment. And for example, this is an example of a failure where this building was built in London as a concave, with a concave facade made of mirrors, so it became like a concentrating lens that melted cars that were actually exposed to this. So it's an example of a design that doesn't basically consider the surrounding very well. So now, we looked at the walls, the roofs, and the road, and together they form an urban canyon. A multiple canyons plus park, they would form the urban canopy, if you want. And when you mix all these facts, the integrated fluxes and response can vary significantly from site to site, as we saw in some of the slides. So for canyons canopy with very little vegetation, usually QH may remain positive during the night, and no dew formation can occur. So this requires the surface temperature. So dew formation would require the surface temperature to go below the dew point temperature, but because there's a lot of heat storage and heat is going out, the surfaces remain quite hot. This is an example of a surface energy budget in central city of Mexico during a cloudless period in the winter. Again, what you notice is that the evaporative cooling is almost zero. Q star is quite large, on the order of 450, and basically all, 2/3 of this energy input is being stored, and only a third is being released at night. Now, notice that what happens during basically the night. So all the storage is being released. Now you notice that the sensible and latent heat become very small at night, because with little turbulence, there's not much basically mixing to drive the heat or moisture away from the surface, so you have very little effective turbulent diffusivity in the atmosphere, so those remain very small. So at night, the QH and QE become very small, and the radiative and the conductive part dominate, and all the storage is now being released during the night. And again, when you try to, for example, look at the nocturnal sensible heat flux density, so this is QH during the night, it's not very large, but you would notice that it very much depends on the volumetric urban density. So it depends on the storage. This is the volume of buildings, so this is the amount of storage related to the amount of storage that you will have. So you would notice that if you're in a very dense location, the sensible heat flux remains positive. So the surface remains hotter than the atmosphere all through the night, and there's heat flux from the surface to the atmosphere all through the night. If you have a much less dense canopy, you get what you expect over a natural terrain, which is basically positive heat flux during the day and negative sensible heat flux during the night. So during the night, the surface is basically cooler than the air, and the surface is absorbing energy from the air. And at intermediate density, you see almost zero, so basically this gives you a neutral atmosphere. The air and surface are at the same temperature, and they don't, as a result, they don't exchange a temperature in a net sense. Now, vegetated canyons can have grass and trees, and they can have a significant impact on urban canyon energy balance. Primarily, they allow water storage that dissipates a lot of the thermal energy through evapotranspiration. Trees have other benefits. They can shade the walls and the ground, and sometimes the roof and the humans, so they contribute a lot to thermal comfort. They can slow wind and turbulence, and that actually might have a negative effect because that can trap pollutants. And they, unlike grass, so grass can evaporate for a couple of days after rainfall because it has very shallow roots. And trees can actually dig much deeper into the soil. They have deeper roots, and so trees can continue to evaporate and give you evaporative cooling benefits even a couple of weeks after a rainfall. So they are quite different from just shallow vegetation. Dense trees can also usually can usually significantly cool the city through all these combined effects. So in this paper, we basically added trees to our urban canopy models. And when we develop, so we take this urban canyon concept and we basically develop it into a actually computational model that you can use. And the first thing, obviously, you want to validate it. So you would validate it by comparing to observations. So in this case, the observations are from a sensor network over the Princeton campus, where the dots are the measured data for asphalt, concrete, and vegetation, and the solid line are the model, and you see that the model matches the observations quite well, and matches the difference between the temperature of the grass, the concrete, and the asphalt. Also, you would notice that the grass is always cooler. Asphalt and concrete are not. Asphalt is hotter during the day, but during the night, asphalt becomes cooler, and concrete becomes hotter because concrete can store a lot of energy, and so it remains hotter all through the night. Also, we can compare the modeled H or QH, so in my nomenclature it's H, to the observed H, and you see that the model can produce the sensible heat flux into the atmosphere quite well. The latent heat flux is more variable and more difficult, but again, and after rain you cannot capture it very well, but again the model captures it quite well. Now actually before I kind of continue, let me tell you a little bit for those who are not familiar with the model. So again, this is kind of a model of the urban canyon concept. So we have a building, we impose the building temperature. We need to basically describe the thermal resistance of the walls and the roofs that determine how much roof or how much ground heat flux is going to happen into the roof and the walls. And then we have temperature of the air and humidity of the air and wind speed at this level that are either given by coupling to an atmospheric model, like the weather research and forecasting model, or by observations. You put a station, a tower, you observe these, and you basically provide them to your urban model. And there are all these resistances, which are basically the degree to which atmospheric turbulence and mixing is aiding, conducting, or resisting the flow of heat between the various facets and the atmosphere. So we have a resistance between the roof and the air, and then inside the canyon we have the canyon air and the resistance to heat flux between the different facets and the canyon air, and between canyon air and the free air above the canyon. And we compute the E and H from the roof and E and H from the canyon, E and H being QE and QH in the nomenclature of both. And basically, when we run this, we can run it over multiple days and look how the urban area is responding. Now, what you observe when you basically apply this to trees is that, again, we have the observation as the dots, and the model in red is with tree, and in dashed blue is without tree. You'll notice that the net radiation is almost the same, with or without tree. So tree don't have a big effect on net radiation. However, when you start, for example, looking at sensible heat, you'll notice that the sensible heat with tree is a little bit lower, and it's lower actually matching the observations a little bit better. For sensible heat, for latent heat, it's a little bit higher with trees. This is a dry area, so latent heat was small, but it's a bit higher, matching the observations better. And you see that actually if you include trees, without tree and with tree, the difference in these lines, it looks small, but it's about 1 degree or 2 degrees of cooling of the canyon air temperature. A degree of cooling is not negligible in the urban context, and again, you see that with trees, it seems to match the observations better. So basically, this kind of supports the fact that including trees in your urban canopy model is important. Now, this is another application of the model over the University of Maryland, Baltimore County campus. And we observed here that there are 4 sectors of the observations. The observation tower is here. And basically, you observed that there are 4 sectors that are different. So this is mainly grass and trees. This is mainly buildings. This is mainly parking, and this is kind of a mixture. So we divided this area into 4 sectors, and we set up the UCM for each of these sectors differently. So this was mainly grass, basically. I mean, almost no buildings. This we take the average buildings and so, building width and building height. This we set it up mainly as asphalt, and this is the mixture. So again, the properties being different, we set the UCM for each sector separately, and then we combine them depending on where the wind is coming from, because if the wind is coming from this direction, the sensor here will mainly pick up signal from this sector. If it's coming from this direction, it will mainly pick up signal from this direction. So, and basically this analysis was the base of these observations. So it turns out that with this analysis, you can represent H and LE quite well. So then we can ask question, okay, so what does this help us learn about material properties in the city? So first, basically, you can observe in the pie chart the distribution of the surface. So basically, this tells us that 22% of my surface is asphalt, 19 is concrete, 33 is green cover, and roofs are 21 and 5% for white and black. And now you can say, okay, so my asphalt is 22%. How much of the H, QH, is given by the asphalt? So even though it's only 22%, it's producing about 45% of sensible heat flux into the atmosphere. So it's a big source of basically the daytime urban heat island. And you'll notice that vegetated areas are 33%, but they hardly produce 10% or less of the sensible heat. Again, this 33% is going to give me about 75% of latent heat. All the evaporation is happening from the green cover. And the storage is mainly going to be from the concrete and the roofs, because in this case, these are old building roofs that are basically concrete. They're not very well insulated. So they store a lot, and that shows up here. And the net radiation, again, you'll notice that the asphalt, because it's dark, it absorbs a lot more. So the net radiation input to the system from the asphalt is disproportionate to its fraction. And you notice that the cool roofs, because they're reflective, at 21%, they hardly produce maybe 15% of the net radiation absorption. So this is the distribution at the land, and this is the distribution in terms of energy fluxes. You see that the two are quite different because of the different properties of these materials. So again, asphalt low reflectivity results in large Rn and then large H. This is kind of the nomenclature that I use in these plots, in these papers, and that map how it maps to oaks. Roofs get longest insulation, and they're also extensive and older, so they absorb a lot of Q. Again, because they have a full sky view factor, this is going to be critical for building cooling loads, the heat flux through the roof. And this might have the smallest area concrete absorbs the highest Q. Of the ground surfaces, not the building. Okay, so again, going back to the properties of concrete and its large thermal effusivity and inertia, which allows it to store heat and remain hot during nighttime, what you observe is that during the day, the concrete is cooler than the black roofs or the asphalt, but during the night, it is actually the hottest material. This is also the same observations for concrete over the Princeton campus. So this was a model. This is a sensor network observation. Again, concrete remains the hotter during the night. And when your model, at least qualitatively, matches your observations, you're usually happy. Okay? Now, evaporation. So evaporation is mainly from the vegetated areas, and this is why some people tend to think, okay, so basically all the evaporation or the hydrology of cities is not important because if they're dry, they're deserts. But as many people have noted, including our group, is that actually cities are not desert, and even though there's little water, it can be very important. For example, in this analysis, we said, okay, how much of the evaporation is from vegetation versus impervious areas? And we observed that 18% of the total evaporation during this month is actually from concrete and roofs that are technically dry, but when it rains, they store a little film of water, and that film of water eventually evaporates. And in this second part of July, it was a very wet month, so it was raining all the time, and these impervious areas still had water on the surface, and you see large LP, and it results in 80% of the evaporation happening from these impervious areas. So this is another study over a green and cool roof. We wanted to compare them to look at the effect of albedo and insulation. So we instrumented the white roof and the black roof, and we put some sensor network there so to kind of collect the data. And these are observations from of the surface temperature. Obviously, you can guess that 1133, this station was the white roof, and those two are the black roofs, and you can see differences of 20 degrees in some cases in the surface temperature between the black and white roofs. This is kind of, okay, so this was the surface temperature. The air temperature, they're really close to each other, and the atmosphere turbulence is a great mixer, so you don't see much difference in the air temperature between those different quantities. Okay? Okay, so we opened the roof, we instrumented, we put some heat flux plate that can measure heat flux into the roof at any height. This is the Princeton Plasma Physics Lab. The engineering team was super helpful. They allow us to open the roofs and work in them. Usually that's not the case. We had 4 roofs of different R values, so different insulation, and different albedo, and so we wanted to see which roof albedo is better, or which roof design is better for Princeton. And when I started this project, I was basically convinced that in Princeton, kind of promoting white roof is not a good idea, because we're dominated by heating and we have to balance the two, and so maybe dark roof is the solution. Now, do you think that that's at the end of the project I changed my mind, or was that the case? Maybe the question is too simple. So what do you think colder area like Princeton or Boston should use, cool or dark roofs? Dark. Okay. So that's what I started by thinking. But it turns out that things are a little bit more complicated. So let's take a look. So this is how much energy is flowing, per meter square per day into the different roofs. So this is a white roof, W at the end. This is a white roof, W at the end. But their R values are changing. Okay, sorry, this is really not legible here. But let me tell you that the one, this is R12, and then this is R31, 31. So this is the insulation, right? So this is R12, this is R30. So these are much more insulated than this one, okay? Sorry, the other way around. This is, so 21, 24, 34, 36, and 48, sorry. Yeah, no, this is the other way. This is the least insulated, and that's the most insulated, obviously. Okay, so let's observe the heat flux in and out, the net one, during basically the different months. And so in means basically, or negative means heat leaving the building, and positive meaning heat going into the building. So negative, you need heating of the building, positive, you need cooling. Okay? So what you first observe is, okay, let's first look at these two graphs. This is the LSP black and LSP white. Both are R24, same insulation. One is black, one is white. What you observe is in the summer, there's a huge difference. The black one is gaining much more heat, and the white one is much better, is gaining much less heat. But during the winter, okay, so the white one is losing more heat, as you expect, but the difference is really minor. It seems like the winter difference in heat gain is much, much smaller. So it seems that the winter time, this benefits or penalty of a white roof is really minor compared to the summertime benefits. So that was kind of curious and interesting. And you observe it, you know, also, for example, you compare this white to this, let's say, black. There's even though they don't have the same R, but you see a lot more benefits in the summer compared to the winter. And obviously, as you insulate more, all your heat fluxes decrease. So this is the heat flux into the building. If you insulate more, all the heat fluxes and losses decrease. So, okay. So then we used what we call the Princeton roof model. Basically, it's the roof component and all of these, by the way, are observations, right? So this is all observations. And we try to use the model to understand what's happening. So this is a plot that shows you, okay, foam thickness, this is the R value, and albedo, as you vary the albedo from 0.5 to 0.75, and this shows you the heat flux in the same units I showed you on the previous graph. Okay, so obviously when you increase your insulation, your heat flux decreases as you expect, hyperbolically in fact, as you can see. However, you see that during the winter month, there is much less difference with albedo. During the summer month, there is a lot of difference with albedo. And so, after we did this project, I kind of understood, we started understanding why. So in the summer, the energy gain, So in the summer, the energy gain from low albedo of dark roof is very important, especially for low R, because albedo is very important during the summer, because in the summer, thank you everybody. So in the summer, you have very long days, and the peak cooling is during the middle of the day where sun is out and the albedo is important. So the albedo is very important for summertime cooling. In the winter, on the other hand, the winter losses are going to be much less sensitive to albedo because the days are shorter, so there's less solar radiation and albedo has less of an impact. And peak heating is during the night where albedo has no impact. So beyond R48, you observe that basically with a lot of insulation, it doesn't matter what the color of your roof is. If you're very well insulated, very little is going to make it into your building. But for less insulation, it turns out that things are not really linear. So the summertime benefits of a white roof are much more than the wintertime benefits of a dark roof. And so as a result, basically we said that even in colder area, you might think about using a high albedo. Now, companies don't like high albedo because high albedo can freeze more easily, has a little bit more challenges in terms of the engineering, but in terms of the thermal performance, I think with our study, at least I was convinced that this is the case. So there's a couple of articles about this work if you want to basically read a little bit more about it. So I'm going to end up with two last things. Electric analogy of heat transfer and basically the 2D energy model. So actually let me I think this is actually, this has to be the big C. This here to write it, this has to be the volumetric one. Otherwise, so C is equal to little cp times rho. Right? This is the volumetric, this is mass, and if you write them like this, I'm sure actually this has to be by volume. Too many definitions, it's confusing. Okay, so let's take a look at the electrical analogy. This should not be showing, it should be hidden, but it's too late now. So okay, let's start with this idea. So the electrical analogy for heat transfer is a very nice way of modeling heat transfer. So have you all taken a course in electric circuits? Electric circuits, resistance, voltage, current. You still remember, I mean, this is like basic physics, right? So the idea with an electric circuit is that you have a driving force that causes basically energy to flow, and that's the voltage difference. And then when you have a voltage difference, you get something to flow, which is the current. The current is an amperes, and basically amperes are coulomb per second. So it's a unit of charge per second going through this wire. Now, you have something driving the flow and something flowing, and how much of flow you're going to get depends on what is what opposes the transport. So the resistance to electric transfer of this wire, and resistance we typically express it in ohm, which is basically volt per ampere. So the current is going to be basically the voltage divided by the resistance. Now, in some circuits also you have something that's called capacitance. So capacitor is a device that actually, as energy tries to flow, it stops it and stores it locally, right? So it basically, usually with a resistive circuit, you impose a voltage, you have a resistance and current flows. With a capacitor, you impose a voltage and you might not have any current because basically you basically are storing this energy or these electrons in the capacitor. So this is kind of how an electric circuit will work, and you can basically have easy equations relating how all these things work together. And so the unit of the capacitance is the farad, which is coulomb per volt. So how much energy or charge you can store per voltage of difference across the capacitance. Now, so this is the electrical, these are electrical circuit, and we do electrical analogs for heat transfer, for hydraulic, basically flow. There's a lot of physical problems where you can draw an analog to the electric circuits and be very effective. In fact, I mean, you know, when we drew these, in your urban canopy models, these are drawn as a resistance. These are drawn as a resistance. That's already an analogy to electric circuits, okay? So now let's take the thermal analog. So in electric circuits, the voltage difference drives the flow of charge. In the thermal analog, a temperature difference drives the flow of energy. In the electrical one, what flows is the charge or the current. Here, what flows is the thermal power. So this is in coulomb per second. This is in basically joule per second. So how much joules are flowing per second, and joule per second is watt, right? Now, here what opposes is the thermal resistance, omega. And here what would oppose it, we have to define some analog called the thermal resistance. And just like here, you can define an electrical conductance, which is 1 over R. We're going to define a thermal conductance, which is 1 over the thermal resistance. So the resistance is phi, and the conductance is lambda. And for so before I move, let's look at this. So the temperature difference is in delta T in Kelvin. The thermal power is in joule per second. The thermal resistance, to have that to be analogous to this, it has to have units of this over that. So it has to have units of Kelvin over joule second. So basically Kelvin over watt. And if you basically look at the properties of the material, you realize that the resistance of the material is going to be the depth or the thickness of the material divided by the electrical or thermal conductivity in this case, divided by the area. So if you divide L by Ka, you basically get units of Kelvin per watt, which are going to define our thermal resistance, which basically tells you that if L is bigger, if the material is thicker, you get more resistance. If the material is more conductive, K goes higher, you have less resistance. And if the material is larger, so you have more area to drive heat flux through, this resistance goes down. So the thermal conductivity and thermal resistivity were kind of intrinsic properties, right? They were per unit mass, or these things are per unit mass, per unit volume, and so on. The resistance and conductance are not. They are properties not of the material only, but of the material and the wall or roof or object you are looking at. Just like this is a property of the resistor, not only the material that the resistor is made of. Okay? So for the thermal capacitance, this is kind of going to be the thermal mass. This is almost related to effusivity. So this is going to be, again, you want it to be in units of
what is flowing divided by, or not ampere, but coulomb. So the what's flowing, so J joules divided by volt, so you, by Kelvin, you want it in joule per Kelvin, and again, if you take the mass times the specific heat, it's going to give you this extrinsic property, which is what we call the thermal capacitance. Now, conductivity and capacitance are material property, conductivity and capacity are material property, conductance and capacitance are material plus element property. And so, for example, if you often define the roof R value, the R value is really the thermal resistance times the area, not the unit area. And so if you think about it, is L over, is phi times A. So phi being L over kappa A, this is L over K. So I changed these slides yesterday and somehow either I didn't save them or I changed the wrong slide. So this is in Kelvin meter squared per watt, which you can think about as Kelvin per watt per meter squared. So what the roof R value really tells you is, given a Kelvin of temperature difference, what is the heat flux in watt per meter squared that I can drive through this wall of a certain thickness, L, okay? And yeah, so how many K of delta T I need to drive 1 watt through a unit area of the roof. Now, let's see. Okay, so I have a duplicate slide here. I'll erase it and erase that. Now, so why is this electrical analogy very nice? I'm going to post actually and share with you a problem where you are basically going to solve something that's a thermal problem as an electric circuit. And it's really very simple and very powerful for solving a lot of simple problems related to urban heat transfer. So beyond that, the last bit of time I'm going to take to introduce you to something called Energy 2D. Have you seen this model before? So it's a really cool model. Let me launch it. It's kind of not something you want to design a building with, but it's a really neat model for brainstorming about things. So this is the model. It's called Energy 2D. You Google it and you download it. It's free. It allows you to construct two-dimensional houses and things and play with them. So in this case, I have a human. You can put thermometers. In this case, I have a black roof and a white roof and a glass roof and glass here. And so let me run this model. So you're going to run it, and I'll tweak it later. You have radiation coming in through basically the glass and being reflected onto the black roof. The black roof is darker, so on the top it absorbs a little bit, it absorbs more than the white roof, so the top surface is warmer. And on the bottom it absorbs more, and also on the bottom, this is kind of a closed space, so the temperature is higher, so, and there's very little advection. So basically the inner temperature goes much higher than the outer temperature. Because there is no advective cooling. You can move this thermometer if I manage to, not managing to, okay, here we go. You can move this up here. You can see that it's 32 on the top and 55 on the bottom, because on the top you have airflow that's basically cooling the surface. And basically you can put thermometers and play games. You can do, for example, you can say heat flux lines. It shows you how the heat is flowing basically, and so on. And you can do like nice things with it. So for example, I can stop and basically say, let me take this material. You right click, you say properties. And okay, so the optical, okay, so you have the geometry, height and all of that. You have, is it a source? This is not a heat source, so this is the roof. So you can make put a heater by making this into a heat source, but I'm not gonna. The thermal property, you give the thermal conductivity, specific heat and density, and optical. So I have an absorptivity of 1 and a reflectivity of 0. I'm going to switch it. I'm going to make the absorptivity 1 and the reflectivity So activity 0. So now I made it into a white roof. Okay? I made it into a white roof. Mechanical and miscellaneous, I'm not interested in them. Now this is the, okay, so now it still looks black, but it's actually, so the properties are that of a white roof view. So the color is only the color, has nothing to do with the properties. I can make it red. Okay? It doesn't matter. So the color is not the properties. And I can basically reset and no, I didn't want to reset. Reset removes my changes. Let me go back here, do optical, change the, oh no, it's still white. Okay. So let me run this. Now both are white. And so both are white. You see that basically you don't get this overheating that you observed before because the material is white. So another thing is now the ground surface here. I made it actually completely absorptive. So I'm gonna go change it and make it reflective. No, this is reflective actually. Let me change it. Let me make it completely absorptive. And let me go back and make this a black roof again. 1 and 0. So I made this into a black roof again, and I'm gonna basically stop and reset and run the model. And now you see basically, because this is absorptive, before it was things were getting reflected and hitting the bottom, and the bottom was basically heating up. But now all the energy is heating is absorbed here, so this heats up, but the bottom of the black roof does not heat. Okay? So you can play, tricks with it, and it has a lot of nice examples. So you can start with, let's say you can do some fluid dynamics, you can do some again, you can, so for example, in this case, I think I started with solar heating example, and I changed it to do what I want. So this one also, let me show you one more thing. So on the fluid side, you can basically click on the fluid and say properties. And okay, so you can pick the medium, sunlight, how you want to model the sunlight. That's not what we want.
You click on the sun.
Say that again.
You click on the sun.
No. So I'm trying to turn off convection. I forgot how to do it. Few options. Okay, I can't remember how to. So in this example, I turned off convection. Convection will simulate airflow. It becomes very slow and sometimes. So this is a really cool one. Students enjoy it. There's another one by the same group called Energy 3D. Now Energy 3D, let's see if I can connect to it. So Energy 3D does not do convection. It only does radiation and diffusion, or maybe only radiation. However, it does radiation in 3 dimensions. So we try to connect. So Energy 3D, I haven't, it's relatively new, I haven't played with it as a lot. It's funded by the National Science Foundation, it's free, and it allows you to do, well, hopefully an image will pop up. But anyway, so I mean, so again, Google Energy 2D or Energy 3D, you can download them and have fun. Okay. So that basically brings us to the end of this lecture. Any questions or thoughts or comments? Yes.
I have one question. First of all, thank you very much. This was very interesting. My question is the model which you present, how it will impact if we test this under extreme weather conditions, especially like extreme cold and extreme heat.
Yes. So let me try to see if I can quickly pop up the example. So I think I have it here. So this is actually, my lab was one of the first one to look at urban heat islands under extreme heat conditions, and the paper, is now my, it's been almost 10 years now, but so this is an example where we coupled the UCM to an atmospheric model and tested it for a heat wave.
Elie, we don't see it.
Oh, good question. I disconnected here. So, so we tested it for extreme heat conditions, and so I don't have all the validation here, but we did validate it. It works well. And what's interesting here to think about is also, this is the extreme heat condition. This is the satellite observation. This is the Worth default UCM. It had very little vegetation, poor hydrological representation, and material properties were not calibrated for the northeast. Here we took the UCM and calibrated the material properties better, still didn't work well. This is our Princeton UCM with all the vegetation and realistic hydrology, and you see it matches very well. So, so far, we have not seen evidence that the performance or validation quality of the UCM is affected by weather conditions. I think it's more affected by the site properties. Some sites are better than others. But if it's good for a site under some condition, it'll probably be still good under all other conditions.
This study you presented is not under heat wave, something like this.
No, so UMPC was, most of the results were from a whole month. So not a, had hot days, cool days, but it wasn't a specific. But this, so if you have a couple of minutes, so we did it for a heat wave, and then we here we did it for a cold wave, and yeah, so we did both extremes actually with our model, but I didn't present much of the results on that.
And just for curiosity, which software do you use?
So the model currently is coded in MATLAB mainly. But I think one of the ex-students tried to create a version in Mathematica, because he liked Mathematica. We don't have it in Python, but I think it could probably be easily translated. Yeah.
How the built environment affect this model? As we see from the result in the built environment, like very big buildings and lot of big structure, complete structure, offer more thermal energy storage. So it's mean what is coming from the atmosphere, we storing it more and reflecting it is very less. So is the built environment is good?
Sorry, which environment?
Built environment.
I mean, you want to make it better, right? So you want to make it better. But the built environment, for example, under, in these cases where the temperature is sub-zero, this plot shows that the cities were 4 degrees warmer than the rural areas. That's very nice, right? That saves you energy, that makes it more comfortable. So they have some wintertime benefits. In the summer, it's not the case. So some of the solutions that Anna Laura and I have been working on, the paper of Claudia, is trying to look for methods to let the heat island be strong in the winter but not in the summer. So things that are adaptable to by season, climate. There's also a lot of variability in the day-to-day weather of the city. So let's see if I can. So this is a heat island observation from New York City. On this day, this is these are simulations. This is not observation. So this is a this is no, these are the Worth simulations. So on a given night, the urban heat island is about 6 degrees, and then 2 days later you have an urban cool island. So there's a lot of fine-scale day-to-day variability of the urban heat island that we don't understand the drivers of. So one of the things we're trying to do now is to think a little bit more about this day-to-day variability, and why is it, on these two, let's say on these let's say these 2 consecutive days, right? Or I think these are the best days, So this day it was plus 4 degrees and the next day it was, minus 1 degree. It looks like it might have to do with insulation or other things, but there's a lot of features we still don't understand.
One more last question.
Yeah.
As you show black roof and white roof, but if the summer time is only 2 months, but the winter time is 6 months, in the 2 months we have more advantages with the white roof, but in the winter, especially in Preston, if we discuss more than 6 months, so black roof will help to reduce the.
So good question. I mean, if you really go to extreme cold conditions, so for Princeton it's not the case, because even for Princeton, you see that we kind of integrated the absolute value of these, and you basically see very little difference in the winter. So there's hardly any benefits. And even in Princeton, for example, we have 5 cooling months and 7 heating months. So it's a little bit more balanced. But the difference, the benefits in the summer are so striking that basically you. And if you get to colder and colder climates, the reality is, if you go to polar regions, northern Sweden, there's no sun in the winter, so you're not going to really get any benefits. So I'm not sure. I'm sure there are some climates where a black roof, especially if you're if you're less insulated, it becomes maybe a little bit more important. But overall, it seems like white roofs are the better solution in most of the world.
Thank you.
Okay. Thank you, everyone.
Thank you.